All right, so as I was saying, with this particular exploration, the introduction to definite integrals, I'm just trying to hone in on what we talked about in the first exploration and the important things that you were supposed to get out of it. Okay, so this particular problem starts out saying, as you drive on the highway, you accelerate to 100 feet per second, so it's not miles. So you're not going but so fast. All right, 100 feet per second to pass a truck. After you have passed, you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity, okay, so that's on the y-axis, as a function of the number of seconds since you started slowing down. So you do need to make sure that you understand the graph, okay? So velocity, that's up the side, right? That's your y-axis. Time, right? Your number of seconds since you started slowing down, that's your x-axis, okay? And you definitely want to make sure that you understand the scale of your graph, okay? So if 60 is up here and 100's there, we got to figure out how are we counting? What is every single block worth, right? So take a look at your graph and tell me how much does each block technically represent as we're going up? What's the count on that? Good. We're technically going up by tens. Very good. Okay. Now, what about the time? What are the time increments? What are the time increments? Each block is 5. Good. 5 seconds. All right. So you do have to make sure that you can interpret your graph. Okay. So number 1 says, what does your velocity, right? So that's velocity, that's your y value, seem to be between time 30 and time 50. Okay? So here's time 30. And I'm just kind of making my way up to the graph so I can see. All right? So I'm going to know, what does my velocity seem to be for that entire time interval? What does the velocity seem to be? Good, Nick. Anybody else? Right, I'm looking for a velocity during this time interval. What does the velocity seem to be? Good, Fuad. Philip, are you there? All right, what do you think the velocity is? Do you agree with Fuad? All right, yeah, okay. So Will, what we're doing right now is we've already started reading through the problem and we're answering number 1, what does your velocity seem to be from time 30 to 50 seconds? And velocity is what the graph is representing, okay? And so the velocity seems to be 60, and that we need units on that. That's feet per second, okay? Now, I want to know, how far do I travel in that time interval, okay? So when I say how far, I want a distance, right? Well, remember we talked about there's a formula for finding distance. Distance equals rate times time. Yeah? So if I want the distance and I know that my rate is 60 feet per second and I'm traveling for 20 seconds, what is my distance? You need an extra 0 there, Will. . right? So 6 times 2 is 12, but yeah, we've got 2 zeros. So it actually ends up being 1,200 feet. Do you notice that the units cancel, right? Seconds are on the bottom here and on the top here, so they cancel. That's how I get feet. Okay, now I want us to explain why the answer to that problem can also be represented by the area, okay, of a rectangular region of the graph. So the rectangular region I'm talking about is the one that I kind of started to form, where I go from 30 to 50, and I create a rectangular region. Okay? All right, well, how would I find the area of that region since it's a rectangle? Length times width, right? Area of a rectangle equals length times width. And it doesn't matter which one I call the length and which one I call the width. All right, so let's do the tall side as the length. What is the tall side? How tall is this rectangle? Forget about that things represent velocity and time. How tall is this rectangle? 60, yeah. And then how wide is this rectangle? 20, good. And so we literally get the same thing, right? So the distance ends up equaling the area of this rectangle. You with me on that? Okay. All right. So it's still 1,200 feet. Okay. Now, let's move on to a different part of the graph. It says the distance you travel between, hold on a second. Oh, I am recording. I thought I had stopped recording. Oh my goodness, or never started. Okay, sorry. The distance you travel between time equals 0 and time equals 20 can also be represented as the area of a region. It's just bounded by the curve of the graph. Okay, so let me so from 0 to 20, I guess technically we could go all the way to 30. All right, but from 0 to 20 is what they're saying. That can also be represented by an area under the graph or bounded by the graph. Well, what I want you to do right now is I want you to literally count the squares in this region, okay? When you get to the pieces that are not whole squares, you're going to estimate the parts to the nearest tenth of a square, okay? So what I mean by that is if you see one like this, okay, where the shaded region represents the part under the curve, so these little pieces that aren't full blocks, all right, you're going to estimate them in terms of tenths, okay? So what do you think this one, like what would you estimate this particular example to be? Like how much of one block? 0.7, okay, maybe 0.6, definitely more than 0.5, but obviously, you know, so maybe 0.6 or 0.7. All right, so I'm going to pause the video while you guys spend some time literally counting up all the whole blocks plus approximating how much you think each piece of a block is and then adding it all up. Okay, so you're just going to count right now. All right, so all I was just saying when I forgot to record was that I had my whole blocks and then I approximated to a nearest tenth what I thought each of the other pieces were, and then I added them all up and got approximately 28.6. Okay? Now, what I want to ask you, or the next question says, how many feet does each small square on the graph represent? So how much does one block, how many feet does one block represent? How many feet is one block? How many feet is one block? Recording. All right, so when I figure out how much each small square is, I'm literally using the units given in the graph, okay? I'm going for 5 seconds at 10 feet per second. 5 seconds times 10 feet per second is 50 feet per block, okay? So now I want to know how far, I know we're approximating, but how far did we go in the time interval that we used in number 3? So from 0 to 20 seconds, if each block represents 50 feet, approximately how far did we go in that 20 seconds? How far did we go in that 20 seconds? Well, what sort of math are you going to use to answer that question? Good, Will. Okay, so it looks like Nick and Will, yeah, you guys are using the 28.6 that I used. That's fine. And then you multiplied it by 50. You can absolutely use the number you got and multiply by 50. We will be a little different from each other. But if you use the 28.6, remember that represented just squares. That was just squares, all right? But then we multiplied each by 50 feet, all right? That's going to give us 1,430 feet, okay? All right, so problems 3 and 4, all right, they just involve finding the product of x values and y values for a function where y may vary with x. Well, that product is called a definite integral of y with respect to x. So based on the units of t and v of t, explain why the definite integral of v of t with respect to t in problem 4 has feet for its units, okay? So what I mean is the definite integral, all right, from, in this case, so we're just going to make it generic from a to b, okay? It would be 0 to 50 for this particular problem. If we take the definite integral from a to b of the velocity, and then the proper notation is times dt, okay? That's your change in time, all right? Y is the answer in feet, okay? So this is my velocity, and this represents time. Why do my units end up being feet? Why do my units end up being feet? Right, because the seconds end up canceling. Because velocity is feet per second, and I'm multiplying by seconds. And mathematically, the time would cancel out. Okay? All right, which just reiterates what I said before. All right, which is why the integral from a to b of v of t dt equals the position at the end minus the position at the beginning of the interval, okay? These are positions or distance, right? Which is feet. So when you integrate a rate, you get a distance or a position, okay? The answer is not another rate. And again, you need to commit that idea to memory, all right? That when you integrate a rate, you go back to position, all right? That's the fundamental theorem of calculus, okay? All right. All right, so this says the graph shows the cross-sectional area, y, in inches squared of a football as a function of the distance, x, in inches from one of its ends, okay? And I want to estimate the definite integral of y with respect to x. Okay? So what that means is I want to approximate, okay? I want to approximate. Our function is technically y with respect to x. So y of x, and then with respect to x means I need to have a dx on it. Okay? So I'm integrating the function of y. X is on my x-axis here with respect to x. And to make it a definite integral, I need to talk about where does the graph start, what x value does the graph start on, and what x value does the graph end on. Okay? So I'm going from 0 to 12. Okay? And so we're going to estimate it. How do you think we're going to estimate that integral? What are we going to do in this picture to estimate that integral? Yeah, the area under the curve. And since we're estimating, we're literally counting those blocks. Absolutely. So please take a couple of minutes to try to figure out, estimate how many blocks are here, okay? But then also keep in mind that it's not just counting blocks. You have to know how much is each block worth. What's the area of one block? Okay, so keep all that in mind. I'll give you a few minutes to work on that. All right. All right, so even though we said roughly 45 blocks, again, we need to know how big each block is. So this definite integral is really going to be whatever number you decided that you got for your count, but then just don't forget to multiply it by 5 because each block is technically 5 units in size, in area. And so I got, and see, that's even a different number than I have on my paper, 225. Okay? So a definite integral is literally the area under the curve. Now, right now, we're just approximating that. When we go back and learn how to actually take an integral, we will be, like, once we know how to do it, it'll give us the exact area under the curve. Okay? Now, what would the units be? What would the units be for this definite integral? Okay? All right, so think about what y of x represented and what x represented. So what was y measured in? The cross-sectional area, inches squared. So y was an area, the cross-sectional area of the football measured in inches squared. Okay? And then dx, that's like your function, that's your distance in x, okay? Well, that's measured, so times distance, that's measured in inches. Yeah, all right. And so what do we get when we do inches squared times inches? Yes, inches cubed, okay? Inches cubed, right? Nothing cancels because none of these are fractions, right? So inches squared times another inches is inches cubed. Well, what would something cubed represent? What would something cubic typically represent? Yes, Will. Three-dimensional, right. What is that like in terms of a measurement? All right. We did area times another measurement. What do we typically get when we have cubic something? All right, Will told me it was volume. Okay, inches cubed, some sort of measurement cubed usually represents volume. Okay, so what do I want you to understand there? Well, if you integrate area, so the integral of an area, okay, actually gives you volume. Because later in this course, we're actually going to be using integrals to find the volume of three-dimensional objects, and we have to integrate an area to get it. Okay? All right, that ends that exploration.